Hi, my name is Zach Schlecht, and I'm the team leader for the Formula Hybrid Powertrain team. This team is part of a larger engineering student organization on campus, the Valpo Motorworks team, or VMW, which is Valparaiso University's chapter of the Society of Automotive Engineers. VMW just started a new project in the fall of 2013, where they are designing and building a Formula-style hybrid vehicle. This project was chosen because of how important having experience with hybrid vehicles is for engineers interested in the automotive field. It is a very fun project that is attractive to current and new members alike. Our senior design team has 6 members, 4 mechanical engineers and 2 electrical engineers, while the Valpo Motorworks team has over 10 additional members. VMW also has another 6-member senior design team working with them and helping with the regenerative braking design. The job of the senior design team is to design, build, and mount the powertrain system. The powertrain system consists of the components that generate power and deliver it mechanically to the road. The major components are an electric motor, a generator, and batteries. The Valpo Motorworks team is responsible for everything else about the vehicle. This year, they were able to design and fabricate the frame of the vehicle, and the steering and suspension systems are designed and ready to build at the beginning of next year.
The goal of our senior design team is to design and build a hybrid powertrain to go on a car to compete in the Society of Automotive Engineers Formula One Hybrid competition. This competition is held every spring and judges the car based on its engineering and handling capabilities.
So one of the major design constraints for this project was budget. We have to work with both the SAE budget given by Student Senate and the budget given by the College of Engineering. Other constraints include the requirements given both by the customer, Professor Newton-Hay, and the SAE Formula Hybrid rules. Our first major design decision was to go with a series configuration. The series configuration runs the vehicle mainly on the motor and uses a generator to recover energy for the rest of the system.
So the propulsion subsystem of our design takes rotational energy provided from the motor and then transfers it to the rear drive shaft through an intermediate jack shaft. This year we'll be going with just a straight fixed gear ratio, although next year when we actually are going to go to competition, this jack shaft will be replaced with a CVT, which will allow us to change gear ratios to optimize our performance throughout the car's RPM range.
The power subsystem consists of the batteries, the generator, a battery charger, and a DC-DC converter. The batteries provide the electrical power to the motor, and our setup consists of 34 3.2-volt cells for a total of 110 volts. The batteries our team decided to go with are the lithium-ion family, which have a very good power-to-weight ratio, and the lithium iron phosphates that we bought are among the safest. The generator is used as a means to recharge the batteries, which will be necessary during the endurance race, since our budget only allowed us to purchase 60 amp-hour batteries, which is on the low end of what our calculations told us was an acceptable discharge rate. The battery charger is the means by which the generator recharges the batteries. The DC-DC converter takes the 110 volts from the battery banks and steps it down to 12 volts for use in the low voltage system.
The brains of our entire system will be the Kelly DC motor controller. This controller will monitor the voltages and currents from the batteries, and based on the potentiometer that will be attached to the throttle, send the appropriate voltage and current to the motor to get the speed and torque we need.
The purpose of the safety subsystem is to keep the driver, bystanders, and judges safe when around our system. This includes both passive and active safety measures. The passive measures include scatter shields and conduit to safely insulate the mechanical and electrical parts. The active parts of our safety system include safety buttons and a battery management system which monitor the electrical components of our system.